A book falls into a black hole. Every atom, every molecule, every word printed on its pages crosses the event horizon and vanishes from our universe. According to the laws of physics, that information should still exist somewhere. But according to Stephen Hawking's calculations from 1974, it doesn't. It's gone. Forever. This isn't just a theoretical puzzle. If Hawking was right, then the fundamental laws governing our reality are broken at the most basic level. The black hole information paradox has haunted physics for nearly 5 decades. It sits at the exact point where our two most successful theories, quantum mechanics and general relativity, collide and produce contradictory answers about the same physical event. One theory says information must be preserved. The other says it's destroyed. They can't both be right. Yet experiments and observations confirm both theories work perfectly within their own domains. What makes this paradox so disturbing isn't just the math. It's what it implies. If information can truly be destroyed, then the universe doesn't make sense in the way we thought it did. The past wouldn't determine the future. Cause and effect would become suggestions rather than laws. Reality itself would be fundamentally random at its core, not just at the quantum level we've grown accustomed to, but at every scale. Picture standing at the edge of a black hole's event horizon. You're holding that book. You toss it in. From your perspective, you watch it fall, getting dimmer and redder as it approaches the point of no return. Time dilation makes it appear to slow down, freeze, and fade. But the book is still there in some sense, its information smeared across the surface of the event horizon like a hologram. At least, that's what one interpretation suggests. Now imagine you could somehow survive falling in with the book. You'd cross the horizon without noticing anything special. No wall, no barrier, no dramatic transformation. Einstein's equivalence principle promises this smooth passage. You and the book would simply continue falling toward the singularity at the center. The information contained in those pages would still exist, at least until you both hit the singularity, and physics as we know it breaks down completely. Two observers. Two completely different stories about the same book. This is where things get weird. The story begins in 1974 when Hawking published calculations showing that black holes aren't actually black. They radiate. This discovery stunned the physics community because it merged quantum mechanics with general relativity in a way no one had done before. The vacuum of space near the event horizon, Hawking showed, isn't truly empty. It seethes with virtual particle pairs constantly popping into and out of existence. Here's what happens. A particle and its antiparticle appear right at the horizon. Normally they'd annihilate each other instantly. But if they appear exactly at the boundary, one might fall into the black hole while the other escapes. The escaped particle becomes real radiation. The infalling particle carries negative energy, slightly reducing the black hole's mass. Over incomprehensibly long timescales, this process causes the black hole to evaporate completely. The actual mechanism is more subtle than this popular explanation suggests. Hawking radiation emerges from how gravity warps spacetime and affects quantum fields. Different regions of curved spacetime can't agree on what constitutes the ground state of a quantum field. This disagreement manifests as real particles and radiation. The mathematics is rigorous. The predictions are precise. And they create an immediate problem. The radiation coming out of the black hole is thermal. Completely random. It depends only on the black hole's mass, charge, and angular momentum. Nothing else. A black hole formed from a collapsing star made of matter produces the same radiation as one formed from antimatter. A black hole that swallowed encyclopedias radiates identically to one that swallowed an equivalent mass of hydrogen gas. All the detailed information about what fell in appears to be lost. This is where quantum mechanics objects violently. Information, in the quantum sense, isn't just facts and figures. It's the complete quantum state of a system. Every particle's position, momentum, spin, and entanglement with every other particle. Quantum mechanics has an iron law called unitarity that states this information cannot be destroyed. Ever. The state of a system at one time completely determines its state at any other time. You can run the equations backward and recover what came before. But Hawking's calculation suggests black holes violate unitarity. They take a pure quantum state, something with complete information, and transform it into a mixed state, something fundamentally random and incomplete. The process isn't reversible. You can't run it backward to figure out what fell in. The information is simply gone. Physicists tried to dismiss this at first. Maybe information escaped somehow. Maybe it's encoded in subtle correlations in the Hawking radiation that were too crude to detect. Maybe the black hole leaves behind a remnant when it finishes evaporating, a tiny stable object containing all the lost information. Each proposal faced severe problems. If information escapes gradually in the radiation, the correlations needed would be impossibly subtle. The radiation from an old black hole would have to be entangled with radiation emitted billions of years earlier. The particles would need to carry more information than their own quantum states allow. The encoding scheme would violate known limits on information density. The remnant idea seems cleaner until you calculate how much information needs to be stored. A black hole can swallow arbitrary amounts of matter and energy. If all that information gets compressed into a tiny remnant at the end, you'd have an object with infinite internal states. That breaks physics in different ways. It suggests an infinite number of particle species could exist, which contradicts everything we observe. For decades, this paradox festered. Hawking himself believed information was truly lost, that quantum mechanics needed modification. Others insisted the problem lay with general relativity or with our understanding of what happens at the singularity. The debate became heated because the stakes were so high. This wasn't just about black holes. It was about whether the universe makes sense at the deepest level. Then in 1997, something shifted. Juan Meldacena proposed the AD/CFT correspondence, a mathematical relationship suggesting that a gravitational theory in a higher dimensional space is exactly equivalent to a quantum field theory on the boundary of that space. The universe, in this view, might be fundamentally holographic. All the information in a volume of space could be encoded on its surface. This idea didn't solve the paradox immediately. But it suggested information couldn't be destroyed because the black hole and its radiation were two different descriptions of the same underlying quantum system. If you had the complete equations governing the boundary theory, you could in principle calculate everything about the black hole's interior and its evaporation. Information would be preserved, though the mechanism remained mysterious. The real breakthrough started coming in 2019. Researchers examining carefully constructed toy models of quantum gravity found that when they properly accounted for quantum entanglement between the black hole and its radiation, something remarkable happened. The entropy of the radiation, which Hawking predicted would increase monotonically until the black hole vanished, instead peaked at the halfway point of evaporation and then decreased back to zero. This pattern is called the Page curve, named after physicist Don Page, who predicted it in 1993. It's exactly what you'd expect if information is preserved. Early in the evaporation, the radiation is mostly entangled with the black hole's interior, so its entropy increases. But after the black hole has radiated away more than half its original mass, something flips. The new radiation becomes primarily entangled with the old radiation that escaped earlier. The system starts behaving like it's purifying itself, converting the mixed state back into a pure state. The key insight involves something called entanglement islands. These are regions inside the black hole that, according to the calculations, should be considered part of the radiation when computing entropy. It sounds bizarre. How can something inside the black hole be part of the radiation outside? But the mathematics of quantum entanglement allows for this kind of non-local connection. The interior and exterior aren't as separate as classical intuition suggests. This recent work hasn't fully solved the paradox. The calculations apply to simplified models that don't capture all the complexity of real black holes in our universe. Critics point out that the results depend on assumptions that might not hold in more realistic scenarios. But the progress has been dramatic enough that many physicists now believe information is preserved, even if the exact mechanism remains unclear. What's fascinating is how the solution seems to require rethinking some of our most basic assumptions about space and time. The interior of the black hole might not be a separate place in the way we normally think about locations. Entanglement, the quantum connection between particles, might actually create geometric connections in spacetime itself. Two entangled particles might be linked by microscopic wormholes, making them in some sense the same object viewed from different perspectives. This gets us to perhaps the most mind-bending aspect of the whole paradox. In trying to understand what happens to information in black holes, physicists have been forced to confront the possibility that spacetime itself isn't fundamental. It might emerge from something deeper, from the patterns of quantum entanglement connecting the universe's fundamental constituents. Space and time could be like temperature or pressure, properties that emerge from underlying dynamics rather than basic building blocks of reality. The implications extend far beyond black holes. If the holographic principle is correct, if information in any volume is encoded on its boundary, then the three-dimensional world we experience might be a kind of projection. The real degrees of freedom, the fundamental information content of the universe, could live on a two-dimensional surface. We'd be living in something analogous to a hologram, though vastly more complex. This isn't science fiction speculation. It's where the mathematics leads when you take quantum mechanics and gravity seriously and try to make them consistent with each other. The black hole information paradox forced physicists to follow the equations into territory that challenges our basic intuitions about reality. But before we can fully appreciate these strange new ideas, we need to understand exactly how black holes work according to general relativity, what Hawking radiation actually is at a deeper level, and why the conflict between quantum mechanics and gravity becomes so acute at the event horizon. That's where our journey really begins. General relativity describes black holes with stunning geometric precision. When a massive star exhausts its nuclear fuel, nothing can prevent gravitational collapse. The star's core implodes, compressing matter to densities that curve spacetime so severely that a boundary forms in the fabric of reality itself. This boundary, the event horizon, marks the point of no return. Cross it and every possible future path leads inward toward the singularity at the center. Einstein's field equations predict this with mathematical certainty. Spacetime becomes so warped near the event horizon that light cones, the regions representing possible future trajectories, tip over completely. Outside the horizon, you can choose to move away from the black hole. At the horizon, staying in place would require traveling at light speed. Inside, even light gets dragged inexorably toward the center. The geometry itself constrains motion in a way that admits no escape. For decades, physicists treated the event horizon as essentially featureless. According to classical general relativity, nothing special happens there from the perspective of someone falling in. An astronaut crossing the horizon of a supermassive black hole wouldn't feel anything unusual at that moment. The tidal forces, the stretching caused by gravity's varying strength across distance, would still be gentle enough to survive. Only later, approaching the singularity, would those forces become lethal. This smoothness at the horizon follows from Einstein's equivalence principle. Freely falling in a gravitational field is locally indistinguishable from floating in empty space. An observer in free fall shouldn't detect any local phenomena marking the horizon's location. The horizon is a global feature of the spacetime geometry, not a local barrier. But quantum field theory tells a different story. In 1974, Hawking applied quantum mechanics to the curved spacetime around black holes and discovered something nobody expected. The vacuum, supposedly empty space, isn't actually empty in quantum theory. Virtual particle-antiparticle pairs constantly pop into existence and annihilate. Usually this happens so quickly it doesn't matter for most purposes. Near an event horizon, though, the extreme spacetime curvature changes everything. Here's what happens at the quantum level. The intense gravitational field can separate these virtual pairs before they recombine. One particle falls into the black hole while its partner escapes to infinity. To a distant observer, this looks like the black hole is emitting radiation. The energy for this radiation comes from the black hole's mass, meaning the black hole gradually shrinks. The popular image of one particle falling in while the other escapes is intuitive but misleading. The actual mechanism is more subtle and involves how observers in different reference frames disagree about what constitutes a particle. An observer falling into the black hole and a distant stationary observer don't share the same notion of the quantum vacuum. What one sees as empty space, the other sees as filled with particles. This observer-dependent nature of particles in curved spacetime produces the thermal radiation. Hawking's calculation showed the radiation follows a precise thermal spectrum, like the glow from a hot object. The temperature depends inversely on the black hole's mass. Stellar mass black holes, several times heavier than the Sun, have temperatures around a millionth of a degree above absolute zero. Supermassive black holes at galactic centers have temperatures billions of times lower still. These are colder than the cosmic microwave background radiation filling space, meaning they actually absorb more energy than they emit and slowly grow. Only tiny black holes, if they exist, would be hot enough to evaporate noticeably. A black hole with the mass of a mountain would have a temperature around room temperature. One with the mass of a large asteroid would glow white-hot. These primordial black holes, if formed in the early universe's extreme conditions, might be detectable today as they reach the final stages of evaporation. The evaporation process accelerates over time. As a black hole loses mass, its temperature rises. Higher temperature means faster evaporation, which increases the temperature further. This runaway process culminates in a final explosive burst of radiation as the black hole disappears completely. The timescale for this process is staggeringly long for astrophysical black holes but becomes rapid in the final moments. This is where the paradox emerges with full force. Hawking's calculation treats the radiation as perfectly thermal, containing no information about what formed the black hole or what fell in. The radiation's properties depend only on the black hole's current mass, charge, and spin. Nothing else matters according to the semi-classical calculation that combines quantum field theory with classical general relativity. Throw an encyclopedia into a black hole. Throw an equal mass of random gas. Once both form black holes of identical mass, charge, and spin, they emit identical Hawking radiation. The information distinguishing the encyclopedia from the gas appears to vanish completely. This violates quantum mechanics' fundamental requirement that information is preserved. The violation becomes absolute when the black hole evaporates completely. In quantum mechanics, if you know a system's initial state precisely, you can predict its final state precisely. The evolution is deterministic and reversible, at least in principle. You could run time backward and recover the initial state from the final state. This property, unitarity, is built into the mathematical structure of quantum theory. But Hawking radiation destroys this reversibility. Start with a pure quantum state, some specific configuration of matter. Let it collapse into a black hole. The black hole radiates thermally and eventually evaporates. You're left with thermal radiation, a mixed state in quantum mechanical terms, that contains no information about the initial configuration. Running time backward wouldn't recover the initial state because that information is simply gone. The conflict runs deeper than a technical inconsistency between theories. It challenges the logical structure of physics itself. Quantum mechanics requires that probabilities of all possible outcomes sum to 1. Information preservation ensures this. If information can be destroyed, probabilities don't add up correctly anymore. The theory becomes mathematically inconsistent. Some physicists initially suggested the information might remain inside the black hole, hidden behind the event horizon. But that doesn't resolve anything. The black hole eventually evaporates completely according to Hawking's calculation. When it's gone, where did the information go? Saying it remained inside just postpones the problem until the black hole disappears. Others propose the information emerges in the final burst of radiation as the black hole evaporates. But calculations showed this would require the radiation to carry impossibly high information density in the final moments. The physics needed to accomplish this would be so extreme it would violate other fundamental principles. The singularity at the black hole's center might seem like a way out. Perhaps quantum gravity effects resolve the singularity and somehow preserve information there. But the event horizon forms before the singularity, and information crossing the horizon can't return according to general relativity. The singularity's fate doesn't affect what happens to information at the horizon. For 2 decades after Hawking's discovery, the paradox remained unresolved. Many physicists suspected something was wrong with the calculation, that some subtle quantum effect was being missed. But the calculation seemed robust. It used well-established physics in a regime where both quantum field theory and general relativity should be valid. The horizon of a large black hole is a region of relatively weak gravitational field strength, where both theories should work. The paradox forces a choice between equally unpalatable options. Accept that quantum mechanics breaks down at event horizons. Accept that general relativity is fundamentally wrong about black hole interiors. Or accept that information can be destroyed, violating the logical consistency of quantum theory. Each option requires abandoning physics principles that have been tested extensively and successfully. What makes this particularly frustrating is that we can't simply observe what happens. The timescales for astrophysical black holes to evaporate are inconceivably long, vastly exceeding the current age of the universe. Direct experimental verification is impossible with current or foreseeable technology. The paradox must be resolved through theoretical reasoning, mathematical consistency, and indirect evidence. The stakes extend beyond black holes themselves. How information behaves in extreme gravitational fields touches on the deepest questions about reality's structure. If spacetime can destroy information, then the universe is fundamentally unpredictable in a way that goes beyond quantum uncertainty. If information is preserved in ways that violate general relativity's predictions, then our understanding of space and time needs radical revision. Either way, something foundational must give. The impasse created space for radical thinking. When conventional approaches fail, physics sometimes advances through ideas that initially seem absurd. In 1997, Juan Meldacena proposed something that appeared mathematically impossible yet turned out to be one of the most important developments in theoretical physics. He discovered a precise mathematical relationship between two seemingly incompatible descriptions of reality. On one side, a theory of quantum gravity in a particular type of spacetime called de Sitter space. On the other, a quantum field theory without gravity living on the boundary of that space. These two theories, despite describing apparently different physics in different numbers of dimensions, turned out to be exactly equivalent. This correspondence, known as AD/CFT, provided the first concrete mathematical realization of a radical idea called the holographic principle. The principle states that all the information contained in a volume of space can be encoded on the boundary of that region, like a hologram that encodes three-dimensional information on a two-dimensional surface. For black holes, this meant something profound. All the information about objects that fell into a black hole might be encoded on the event horizon itself, not lost inside. The horizon becomes a kind of information storage medium, preserving everything in a scrambled but recoverable form. This wasn't just philosophical speculation. The AD/CFT correspondence provided actual equations physicists could work with. In the quantum field theory living on the boundary, information is manifestly preserved because it's just quantum mechanics without gravity. No black holes exist in that description. If the correspondence is truly exact, and the two theories are completely equivalent, then information must also be preserved in the gravitational theory that does contain black holes. The problem is that Hawking's calculation predicting information loss also seemed correct within its domain of validity. Something subtle had to be wrong with it, some quantum effect not captured in the semi-classical approximation Hawking used. But identifying exactly what was missing proved extraordinarily difficult. Progress came from examining what happens to quantum entanglement as a black hole evaporates. Two particles are entangled when measuring one instantly affects the other, regardless of distance. Einstein called this spooky action at a distance and found it deeply troubling. But quantum mechanics insists entanglement is real, and experiments consistently confirm it. When Hawking radiation forms, pairs of particles are created near the horizon. One falls in, one escapes. Hawking's original calculation treated these particles as independent once separated. The escaping particle carried no information about what fell into the black hole. That's why the radiation appeared purely thermal. But quantum mechanics suggests the particle pairs should remain entangled. The outgoing particle correlates with its partner inside the black hole. This entanglement might encode information about the black hole's interior in subtle correlations within the Hawking radiation. Not in any single particle, but in the collective pattern of many particles over time. In 1993, Don Page calculated how this entanglement should evolve if information is truly preserved. Early in evaporation, entropy of the radiation should increase as more particles are emitted. But once the black hole passes the halfway point, having radiated more than half its original mass, something dramatic should happen. The entropy should peak and then decrease, eventually returning to zero when the black hole completely evaporates. This prediction, now called the Page curve, became a benchmark for any proposed solution to the information paradox. If your theory reproduces the Page curve, information is preserved. If it predicts monotonically increasing entropy like Hawking's original calculation, information is lost. For decades, nobody could derive the Page curve from first principles. The AD/CFT correspondence suggested it must exist, but actually calculating it required understanding quantum corrections to Hawking's semi-classical result. Those corrections seemed impossibly complicated. Then in 2019, a group of physicists made a breakthrough using the concept of entanglement islands. They realized that when calculating the entropy of Hawking radiation, you need to include not just the radiation itself but also a region inside the black hole that's maximally entangled with it. This interior region, the island, effectively belongs to the radiation for the purpose of calculating entropy. Early in evaporation, no island exists. The entropy calculation includes only the radiation outside, and entropy increases. But after the page time, an island forms inside the black hole. Including it in the calculation causes the entropy to decrease, exactly reproducing Page's prediction. The island doesn't physically move from inside to outside. Information doesn't escape through the horizon in any conventional sense. Instead, the quantum state of the radiation becomes increasingly entangled with specific regions inside the black hole. This entanglement effectively transfers the information content outward without anything crossing the horizon. It's like having a book torn in half. Each half alone seems to contain partial, incomplete information. But if the two halves are perfectly correlated, knowing one half tells you everything about the other. The information exists in the correlation itself, not localized to either piece. This resolution depends crucially on quantum entanglement having geometric properties. The entangled particles inside and outside the black hole aren't just abstractly correlated. They're connected through the structure of spacetime itself in ways that classical general relativity doesn't capture. Some physicists have proposed that entanglement might actually create geometric connections. Einstein and Nathan Rosen discovered in 1935 that general relativity allows solutions containing wormholes, shortcuts through spacetime connecting distant regions. These Einstein-Rosen bridges seemed like pure mathematical curiosities with no physical relevance. But Melda Sena and Leonard Susskind suggested in 2013 that Einstein-Rosen bridges and Einstein-Podolsky-Rosen entanglement might be the same thing. Whenever two particles are entangled, they're connected by a tiny wormhole. The quantum correlation is the geometric connection. This ER equals EPR conjecture remains controversial and unproven. But it suggests something profound about the relationship between quantum mechanics and spacetime. Maybe spacetime itself emerges from entanglement. The geometry of space isn't fundamental but rather a macroscopic manifestation of quantum correlations between microscopic degrees of freedom. If true, this would completely invert our understanding of reality structure. We normally think of particles existing in space, moving through time. But perhaps space and time emerge from the quantum relationships between particles. Geometry is derived, not fundamental. This perspective offers a potential resolution to the information paradox. Information isn't lost because the interior and exterior of a black hole aren't truly separate regions. They're connected through quantum entanglement in ways that transcend the classical geometric picture of an impenetrable horizon. The information is simultaneously inside and outside, existing in the correlation structure rather than localized to any particular region. These ideas remain at the cutting edge of theoretical research. The calculations work in simplified models, but extending them to realistic black holes in our universe presents enormous technical challenges. The ADS/CFT correspondence applies to anti-de Sitter spacetimes, which have different properties than the expanding universe we actually inhabit. Yet the insights gained have convinced most theoretical physicists that information is preserved. The exact mechanism remains debated, but the weight of evidence from multiple approaches points toward unitarity holding even for black holes. Quantum mechanics wins this round against classical general relativity. That victory comes with a cost. If information is preserved through mechanisms like entanglement islands or ER equals EPR, then the classical picture of a black hole's interior requires revision. The smooth, empty space that general relativity predicts inside the horizon might not exist in the way we thought. This brings us to another puzzle that emerged from trying to resolve the information paradox. In 2012, four physicists, Ahmed Al-Mhairi, Donald Marolf, Joseph Polchinski, and James Sully, discovered a new problem while exploring these quantum corrections. Their finding, now called the firewall paradox, suggested that preserving information might require something even more radical than anyone expected. The AMPS team wasn't looking for trouble. They were trying to verify that the clever solutions to the information paradox actually worked when examined closely. What they found instead shook the foundations of black hole physics. Start with an old black hole, one that's radiated away more than half its original mass through Hawking radiation. The early radiation is long gone, scattered across the universe. New radiation continues streaming out from the horizon. According to quantum mechanics, this new radiation must be entangled with the old radiation to preserve information. That's how the information gets out, encoded in correlations between particles emitted at different times. But there's a problem. Hawking's original calculations showed that particles emerging as radiation are entangled with their partners falling into the black hole. This entanglement across the horizon is what makes the radiation thermal and what creates the smooth, empty space that an infalling observer experiences. No drama at the horizon, just peaceful crossing into the interior. Here's where things break. A fundamental principle of quantum mechanics called monogamy of entanglement states that a quantum system can be maximally entangled with only one other system. If particle A is maximally entangled with particle B, it cannot also be maximally entangled with particle C. The entanglement resource is finite and exclusive. The radiation particle emerging from an old black hole faces an impossible choice. It needs to be entangled with its partner behind the horizon to maintain a smooth horizon. It also needs to be entangled with earlier radiation to preserve information. Both simultaneously, both maximally. Quantum mechanics forbids this. Something has to give. AMPS argued that preserving information requires breaking the entanglement between outgoing radiation and the black hole interior. But breaking entanglement between previously correlated quantum systems releases energy. Enormous amounts of energy. The result would be a wall of high-energy particles at the event horizon. Not inside where nobody outside can see it. Right at the horizon itself. They called it a firewall, a searing barrier that would incinerate anything attempting to cross. This contradicts Einstein's equivalence principle, one of the foundational pillars of general relativity. The equivalence principle states that free fall is indistinguishable from floating in empty space. An observer falling toward a black hole shouldn't notice anything special when crossing the horizon. Local physics should look the same everywhere. A firewall destroys this principle completely. An astronaut falling toward an old black hole would be vaporized at the horizon, experiencing something dramatically different from empty space. The horizon becomes a physical surface with extreme properties, not just a geometric boundary. AMPS laid out the options starkly. Physicists must abandon one of three cherished principles. Give up the equivalence principle and accept firewalls. Give up unitarity and accept that quantum mechanics fails for black holes. Or give up quantum field theory and curved spacetime, the framework underlying Hawking's calculation. None of these options is appealing. Each represents a fundamental revision to physics as we understand it. The equivalence principle has been tested extensively and forms the basis for general relativity. Unitarity is central to quantum mechanics and has never been observed to fail. Quantum field theory successfully describes particle physics and has been confirmed in countless experiments. The firewall paradox sparked intense debate. Some physicists argued that firewalls must exist, that preserving information requires this radical departure from Einstein's predictions. Others searched desperately for ways to avoid the conclusion, looking for subtle errors in the argument or overlooked possibilities. One proposed escape route involves the idea that the horizon's location might be observer-dependent in ways not captured by classical general relativity. Maybe the firewall exists for distant observers but not for infalling ones. This sounds like black hole complementarity. Different observers see different but equally valid descriptions. But complementarity was precisely what AMPS showed breaks down for old black holes. By the time a black hole has evaporated past its page time, there isn't enough entanglement left at the horizon to maintain complementarity. The Hilbert space is exhausted. The information has to be somewhere, and all the logical options lead to contradictions. Another possibility involves modifying what happens deep inside the black hole rather than at the horizon. Perhaps the singularity isn't a point of infinite density but a region where quantum gravity effects create a bounce, turning the black hole into a white hole. Information could escape through this future transition rather than gradually through Hawking radiation. This pushes the problem elsewhere but doesn't fully resolve it. Even if information eventually exits through a white hole, the accounting during the evaporation process still presents challenges. The page curve still needs to be explained. The entanglement structure still faces the monogamy constraint. Some researchers propose that Hawking radiation might not be exactly thermal even initially. Perhaps subtle correlations exist from the start, correlations too small to detect in Hawking's semi-classical calculation but crucial for information preservation. These correlations could carry information out gradually without requiring the late-time entanglement switches that create the firewall. This approach requires understanding black hole quantum states in far more detail than current theory allows. The calculation would need to include quantum gravity effects that we don't know how to compute. It's a promissory note, maybe future theory will reveal these correlations. The ER equals EPR conjecture offers another perspective. If entangled particles are connected by wormholes, maybe the distinction between interior and exterior becomes less sharp. The radiation particles and interior partners aren't separately entangled with two different systems. They're connected through geometric channels that transcend the simple horizon boundary. This is elegant but raises new questions. How do these microscopic wormholes connect to macroscopic geometry? What happens to them as the black hole evaporates? Do they grow, merge, or dissolve? The mathematics of quantum entanglement doesn't automatically translate into spacetime geometry. Recent work using quantum information theory has provided some insights. Researchers discovered that calculating entanglement entropy in specific models requires including contributions from regions inside the black hole, the so-called entanglement islands. These islands change the accounting in ways that might resolve both the information paradox and the firewall paradox simultaneously. The island formula modifies how we calculate the entropy of Hawking radiation. Instead of computing entropy only from the radiation itself, we include contributions from regions inside the horizon that are quantum mechanically connected to the radiation through entanglement. This connection is subtle, involving quantum extremal surfaces rather than classical boundaries. When islands are included, the entropy follows the page curve. It increases initially, peaks around the page time, then decreases back to zero. This happens because the island contribution becomes dominant after the page time, effectively transferring the entropy accounting from the radiation to the interior radiation system. This resolves information loss. It might also resolve the firewall. If the radiation is properly entangled with the island region inside the horizon, the monogamy constraint is satisfied differently. The radiation isn't maximally entangled with both old radiation and interior partners separately. Instead, the old radiation, new radiation, and island form a tripartite entangled state where monogamy is respected. The horizon remains smooth because the entanglement structure doesn't require violent energy release. Information preservation doesn't demand breaking correlations at the horizon. It's encoded in the global quantum state structure, which includes both interior and exterior regions in subtle ways. But this resolution works cleanly only in simplified models. Extending it to realistic black holes in our universe requires solving quantum gravity in de Sitter space, which remains beyond current capabilities. The models where islands work use anti-de Sitter spacetime with special boundary conditions that don't match our expanding universe. The firewall debate continues because these fundamental questions remain unresolved. We still don't have a complete theory of quantum gravity. We can't calculate exactly what happens at black hole horizons when quantum effects become important. We're forced to extrapolate from partial theories and simplified models. What's clear is that something in our understanding must change. Either the smooth horizon predicted by classical general relativity is wrong, or our understanding of how quantum information behaves near horizons is incomplete, or both theories require modification in ways we haven't yet imagined. The paradox has become a testing ground for proposed theories of quantum gravity. Any candidate theory must address the firewall. String theory, loop quantum gravity, emergent gravity, they all need to explain what happens at the horizon of an old black hole without violating fundamental principles. This isn't just abstract philosophy. The paradox probes the deep structure of reality at the intersection of quantum mechanics and gravity. Resolving it will require understanding how spacetime emerges from quantum entanglement, how information is encoded in gravity, and what replaces classical geometry at Planck scales. The firewall forces us to confront uncomfortable possibilities. Maybe horizons aren't smooth. Maybe equivalence fails in extreme conditions. Maybe information preservation requires mechanisms we haven't conceived. Each option demands rethinking physics at its most fundamental level. Beyond these competing frameworks, another perspective has emerged that reframes the entire problem. Instead of asking which theory is right, some physicists question whether the paradox itself rests on false assumptions. Consider what we actually know versus what we assume. We've never observed Hawking radiation. We've never watched a black hole evaporate. Our theories extrapolate from regimes where they're tested to extreme conditions where they might break down. Every resolution requires believing something counterintuitive about reality. The ER equals EPR conjecture exemplifies this strangeness. Proposed by Juan Meldacena and Leonard Susskind in 2013, it suggests that quantum entanglement and wormholes are the same phenomenon viewed from different perspectives. When two particles become entangled, they're connected not just through abstract quantum correlations, but through actual geometric connections in spacetime. Think about what this means. Every entangled pair in the universe might be connected by a microscopic wormhole. The quantum correlations we measure in laboratories might reflect genuine geometric links threading through space. Entanglement wouldn't be spooky action at a distance, but traversable connections through spacetime's fabric. Applied to black holes, this resolves the firewall in an unexpected way. The radiation leaving the black hole stays entangled with particles inside through these wormhole connections. There's no monogamy violation because the connections form a complex network rather than independent pairings. The interior and exterior remain linked through spacetime geometry itself. But this raises new questions. What are these wormholes made of? How do they form? Why can't we traverse them to send information faster than light? The proposal trades one mystery for another, replacing quantum paradoxes with geometric ones. Some physicists find this unsatisfying. Others see it as profound. If space-time geometry emerges from entanglement patterns, then space itself isn't fundamental. The distances between objects, the fabric of reality, might be secondary phenomena arising from quantum information structures. This connects to the holographic principle in unexpected ways. If the universe is holographic, with all information encoded on boundary surfaces, then space-time volume might be an illusion. The wormholes connecting entangled particles could be the mechanism through which the hologram creates the appearance of three-dimensional space. You're watching reality's basic architecture get questioned at the deepest level. Not just how particles behave or how gravity works, but whether space and time are real in any meaningful sense. Loop quantum gravity takes a different approach to these questions. Instead of starting with string theory and extra dimensions, it quantizes spacetime itself. Space becomes granular at the Planck scale, composed of discrete units rather than being continuous. In this framework, black hole singularities might not exist. The equations that predict infinite density and curvature break down when spacetime becomes quantized. Instead of crushing to a point, matter might bounce, potentially creating a white hole on the other side. This offers another resolution to the information paradox. Information doesn't get destroyed or released through subtle quantum correlations. It passes through the black hole and emerges from a white hole, possibly in another universe or another region of spacetime. The paradox dissolves because the black hole isn't actually a final state. But white holes have never been observed. They might be mathematical artifacts rather than physical objects. And even if they exist, does information emerging in another universe count as preservation? If we can't access it, does the distinction matter? These competing proposals reveal how far we are from consensus. Each framework makes different assumptions about what's fundamental. String theory assumes strings in extra dimensions. Loop quantum gravity assumes quantized spacetime. The holographic principle assumes boundary bulk duality. None of these assumptions are proven. What's remarkable is that all these approaches might be partially correct. They could describe different aspects of a deeper theory we haven't discovered yet. The firewall might be real in some sense while information is preserved in another. Complementarity might hold in certain situations while failing in others. Physics has encountered this before. Light behaves as both wave and particle depending on how you measure it. The contradiction resolved only when quantum mechanics revealed a deeper framework encompassing both descriptions. The black hole paradoxes might require a similar conceptual leap. Some proposals get truly radical. What if the interior of old black holes simply doesn't exist? Not because it's destroyed, but because it never formed in the first place. The holographic principle suggests the interior might be a redundant description, with all real degrees of freedom living on the horizon. This seems absurd. We see matter fall into black holes. Surely it goes somewhere. But remember, we only see things approach the horizon. We never see them cross it. An external observer watches objects freeze at the horizon, never quite reaching it due to extreme time dilation. From the falling object's perspective, it crosses smoothly and hits the singularity. But if that perspective isn't physically realized, if the interior exists only in a description that never actually occurs, then there's no place for information to be lost. It remains encoded on the horizon, exactly as holography suggests. This resolution requires abandoning the idea that all reference frames are equally real. The external observer's perspective becomes fundamental, while the infalling observer's experience becomes an approximate description valid only in certain limits. Einstein would have hated this. Relativity treats all observers as equally valid. No frame is privileged. But quantum mechanics and holography might force us to choose. When you combine them with gravity, observer equivalence might break down. The implications extend beyond black holes. If different observers don't share a single objective reality, what does that mean for the universe as a whole? Are there facts about the cosmos that depend on who's measuring them? Does reality itself become observer-dependent at the deepest level? These aren't just abstract questions. They affect how we understand the Big Bang, the universe's ultimate fate, and whether parallel universes exist. Black holes become laboratories for testing the nature of reality itself. Recent work on quantum complexity adds another dimension to the paradox. Complexity measures how difficult it is to reconstruct a quantum state from basic operations. For black holes, complexity grows for exponentially long times, far longer than any other known physical process. This suggests something profound about black hole interiors. Even after they've radiated away most of their mass, even after the page time when information supposedly starts emerging, the interior might still be evolving in increasingly complex ways. The scrambling of information doesn't stop. It continues, creating states of higher and higher complexity. What does this mean for information recovery? If the black hole's interior becomes exponentially complex, extracting information from Hawking radiation might require exponentially difficult computations. The information is technically there, encoded in subtle correlations, but practically inaccessible. This doesn't violate unitarity. The information isn't destroyed. But it might be irretrievable in any realistic sense. You'd need to collect and analyze Hawking radiation for times longer than the universe's age, using computational resources exceeding what's physically possible. Does this count as resolving the paradox? Technically, yes. Practically, maybe not. The information is preserved in principle but lost in practice. Physics usually distinguishes between these cases, but quantum mechanics blurs the line. If recovering information requires more resources than exist in the universe, is it meaningful to say it's preserved? These questions have no clear answers yet. What's certain is that black holes force us to confront the limits of physical law. They sit at the boundary between classical and quantum, between gravity and information, between what we can observe and what we can only theorize about. Every proposed resolution requires accepting something that seems impossible. Firewalls violate equivalence. Complementarity violates uniqueness. Wormholes violate our understanding of entanglement. Remnants violate energy conservation. Each solution creates new problems while solving old ones. Maybe that's the real lesson. Nature doesn't care about our intuitions or our preference for simple answers. The universe operates according to rules we're still learning to comprehend. Black holes reveal the gaps in our understanding, the places where our best theories fail. They're not just objects in space. They're signposts pointing toward deeper truths about reality's structure. The paradoxes they create aren't bugs in our theories but features revealing where those theories need to grow. Where does all this leave us? Standing at the edge of physics itself, staring into an abyss that stares back with equations we can barely write. The black hole information paradox isn't just an academic puzzle. It's a crack in the foundation of everything we thought we understood about reality. For nearly 50 years, the brightest minds in physics have thrown themselves at this problem. Some emerged with revolutionary ideas. Others retreated, convinced we're asking the wrong questions entirely. Consider what's actually at stake here. We're not debating details. We're questioning whether the universe makes sense at its most fundamental level. Can nature simultaneously respect quantum mechanics and general relativity? Or must one of them break? String theorists believe they've found the answer through entanglement islands and the Page curve. Loop quantum gravity researchers point toward remnants and modified horizons. Higher dimensional geometry suggests information hides in extra dimensions we can't perceive. Each approach claims victory. Each leaves something unexplained. The truth might be stranger than any of them imagine. What if black holes aren't revealing flaws in our theories but showing us that reality operates on principles we haven't discovered yet? The paradox might not need solving. It might need reframing. Think about how often this happens in physics. Maxwell's equations seemed incomplete until relativity showed that electricity and magnetism were unified. Quantum mechanics appeared inconsistent with determinism until we accepted that nature is fundamentally probabilistic. Wave-particle duality made no sense until we realized particles and waves were human categories, not nature's. Black holes might be doing the same thing now. They're not broken. Our concepts are. The firewall paradox illustrates this perfectly. We're forced to choose between equivalence, unitarity, and quantum field theory. But why assume any of them survive unchanged at a black hole horizon? These principles work beautifully in the regimes where we tested them. Near absolute extremes of gravity and quantum mechanics, maybe they transform into something else entirely. Spacetime itself might be emergent. The ER equals EPR conjecture hints at this. If entanglement creates geometric connections, if quantum correlations literally build the fabric of space, then asking whether information falls into a black hole becomes meaningless. There's no independent stage called spacetime on which events unfold. The stage is made of the same quantum stuff as the actors. This flips the paradox on its head. We've been asking how information escapes from a region of spacetime. But if spacetime emerges from quantum entanglement, information never went anywhere. It was never trapped because there's no fundamental distinction between inside and outside. Those are classical concepts applied where classical thinking fails. The holographic principle pushes this further. Information about a volume is encoded on its boundary. Not metaphorically. Actually encoded, like data on a hard drive. The interior might be a kind of projection, a hologram reconstructed from surface information. If that's true, black hole interiors might not exist the way we imagine. When matter crosses the horizon, it doesn't enter a separate region. It becomes part of the boundary information. The interior we calculate might be a mathematical convenience, not a physical place. This sounds absurd until you remember that quantum mechanics already told us location isn't fundamental. Particles don't have definite positions until measured. They exist as probability clouds, as potential rather than actual. Why should regions of space be different? The Beakenstein bound makes this concrete. A volume can only hold so much information before it collapses into a black hole. That limit scales with surface area, not volume. Physical law itself enforces holographic encoding. Nature won't let you pack information three-dimensionally beyond a certain threshold. What does this mean for consciousness? For observers? If reality is holographic, if volume is illusory, then where are we? Our subjective experience feels three-dimensional. We move through space that seems genuinely volumetric. Yet the laws of physics suggest this might be a useful fiction, a cognitive model rather than fundamental truth. Black holes force us to confront this. They're not just astrophysical objects. They're philosophical weapons, demolishing assumptions we didn't know we were making. The complexity growth inside black holes adds another layer. Even after the page time, even after information supposedly starts escaping, the interior continues evolving toward states of exponentially increasing complexity. This scrambling never stops. It continues for timescales that dwarf the universe's age. So yes, information might be preserved in Hawking radiation. Technically, unitarity holds. But practically, the information is scrambled so thoroughly that extracting it would require computations exceeding the universe's total information processing capacity. You'd need to collect every photon of Hawking radiation, track every quantum correlation, and solve equations more complex than anything physically possible. Is that a resolution? Information exists in principle but is irretrievable in practice. Physics doesn't usually make this distinction matter. But at black hole horizons, maybe it does. Maybe the universe draws a line between theoretical and actual. Maybe some information is preserved in a technical sense while being destroyed in every practical sense. This connects to deeper questions about determinism and free will. If the universe's state at one moment determines all future states, then information about the past must persist. But if accessing that information requires impossible computations, does it matter? The future might be determined yet unpredictable. Fixed yet unknowable. Black holes crystallize this tension. They're perfect laboratories for testing what determined really means when quantum mechanics and gravity collide. And we're just beginning. Every resolution proposed so far requires accepting something that seems impossible. Firewalls demand we abandon equivalence. Complementarity forces us to give up observer independence. Remnants violate energy bounds. Wormholes stretch entanglement beyond recognition. Each solution trades one impossibility for another. Maybe that's the message. Maybe reality at its deepest level refuses to fit into human categories. Our job isn't to solve the paradox but to build new frameworks where it dissolves. The next generation of physicists will likely find answers we can't currently imagine. They'll have tools we haven't invented, mathematics we haven't discovered, experiments we can't yet perform. They might look back at this era and wonder why we found it so confusing. Or maybe not. Maybe the information paradox remains forever at the edge of human understanding, a koan that transforms each generation of physicists who wrestle with it. What we know now is this: black holes are not just collapsed stars. They're windows into quantum gravity, laboratories for testing spacetime's limits, paradox engines that reveal where our theories break down. They connect thermodynamics to geometry, quantum mechanics to cosmology, information theory to gravity. Every black hole in the universe is simultaneously simple and impossibly complex. Described by three numbers yet containing information that might fill libraries. Thermal yet quantum. Eternal yet evaporating. Empty yet full. They're cosmic Zen masters, teaching through contradiction. The lesson isn't about black holes. It's about reality. About what exists, what we can know, and where those two categories diverge. The paradox remains. The mystery deepens. And somewhere in the darkness, information either falls or doesn't, exists or vanishes, waits or transforms. We're still learning which. That uncertainty itself might be the point. Physics advances not by answering questions but by learning to ask better ones. Black holes ensure we never stop asking. We've traveled from thermal radiation at event horizons to wormholes connecting entangled particles, from firewalls that might incinerate reality to islands that preserve information through geometric sleight of hand. Each step revealed how little we actually know about the universe's fundamental structure. The information paradox stands unresolved not because physicists lack intelligence or effort, but because it's asking questions reality might not answer in ways we expect. We demand to know whether information is destroyed or preserved, whether horizons are smooth or violent, whether spacetime is fundamental or emergent. Nature responds with equations that work mathematically but strain comprehension. Here's what makes this genuinely unsettling. Every resolution requires abandoning something we thought was bedrock. String theory saves information by making spacetime holographic, suggesting the three dimensions we experience are projections from a two-dimensional surface. Loop quantum gravity eliminates singularities by quantizing space itself, turning smooth geometry into discrete chunks. The ER equals EPR conjecture fuses quantum mechanics with gravity by making entanglement geometric, connecting particles through microscopic wormholes. These aren't minor adjustments. They're wholesale revisions of what we mean by space, time, and information. And they're all incomplete. The calculations work in simplified models that don't match our universe. The predictions can't be tested with current technology. The implications cascade into territories where mathematics becomes speculation. Yet progress is real. The page curve derivation from entanglement islands represents genuine advance, even if it doesn't apply directly to astrophysical black holes. The ADS/CFT correspondence provides concrete mathematical tools for exploring quantum gravity, even if the spacetime involved isn't ours. These partial victories suggest we're circling something true, even if we can't yet see it clearly. The complexity growth inside black holes might be the most important clue we have. Information scrambles so thoroughly, so completely, that recovering it becomes practically impossible even if theoretically allowed. This hints that physics draws distinctions we haven't formalized between information that exists and information that matters, between states that are determined and states that are knowable. Quantum mechanics already showed us that reality depends on measurement, that observation isn't passive but participates in creating what we observe. Black holes push this further. They suggest that at extreme scales, the universe might not just be observer-dependent but observer-defined. Different perspectives might not just see different things but actually inhabit different realities, with no privileged frame to adjudicate between them. This challenges the scientific enterprise itself. Science assumes an objective reality that exists independent of observation. We discover laws, we don't create them. But if black holes show that observer independence fails, if complementarity requires contradictory descriptions to both be true, then what does scientific truth even mean? Maybe we're approaching the limits of what physics can explain using human concepts. Language evolved to describe medium-sized objects moving at medium speeds. Mathematics extends our reach, but even math uses concepts like space, time, and causation that might be provisional rather than fundamental. The paradox might be showing us that reality doesn't fit into any framework built from human intuition, no matter how abstract. We need new mathematics, new logic, new ways of thinking that we can't currently imagine. The resolution might be literally unthinkable with our current cognitive tools. Or maybe the paradox is teaching us humility. For 3 centuries, physics has been almost unreasonably successful. We've explained phenomena from subatomic particles to galactic clusters using theories that fit together with stunning precision. Black holes are the first place where that success breaks down completely, where our best theories contradict each other and themselves. This might be healthy. It reminds us that understanding the universe is an ongoing project, not a finished product. Every generation believes they're close to a final theory. Every generation discovers new mysteries that demonstrate how much they didn't know. the physicists currently wrestling with the information paradox won't solve it completely. They'll make progress, derive important results, develop new techniques. But the full resolution will likely require insights from future researchers working with concepts we haven't invented yet. That's not failure. That's how science works. Each generation builds on the previous one, climbing higher to see further. The view from our current position reveals black holes as perhaps the most important objects in the universe for theoretical physics. Not because they're common or directly observable in detail, but because they mark the boundary where our understanding ends. Beyond that boundary lies quantum gravity, the theory that will finally unite quantum mechanics and general relativity into a coherent framework. Whether that framework involves strings, loops, holography, or something we haven't conceived doesn't matter as much as the fact that black holes are showing us it's necessary. The information paradox is a signpost. It's telling us that spacetime is probably not fundamental, that information plays a deeper role in physics than we realized, that the universe's structure at Planck scales will surprise us as much as quantum mechanics surprised physicists a century ago. We don't know if firewalls exist. We don't know if black hole interiors are real. We don't know if information is truly preserved or just appears to be from certain perspectives. What we do know is that answering these questions will require revolutionizing our understanding of reality itself. That's where we stand. At the edge of knowledge, staring into black holes that stare back with mysteries we're just beginning to comprehend. The paradox isn't solved. The journey isn't finished. And somewhere in the mathematics we haven't yet written, in the experiments we haven't yet performed, in the insights we haven't yet had, the answer waits. Not the answer we expected. Not the answer we wanted. But the answer the universe has been trying to tell us all along, if only we learn to listen in the right language.